This lesson deals with supplemental problem 8.9. You can find this problem in the ECE202 ebook in the Chapter 8 Supplemental Problems on page 8. In ECE201 in section 7.4, we found the complete response of a parallel RC circuit with a cosine input function. This was the complete response, which included the transient response and the steady state. What we'll do in this problem is try to find the steady state response, which is this term right here, using phasors. Let's use our three-step algorithm. So step one is to transform from the time domain to the frequency domain. Our phasor then is a magnitude of I sub A at angle 0. Resistor is still a resistor, and now the capacitor is 1 over j omega c. And the voltage V of t now becomes the phasor voltage V. So let's find the parallel combination of these two impedances, and then we'll pump that current into it and get the voltage V. Okay, so V is then equal to Z equivalent, which is the impedance between these two input terminals, and we'll multiply that by the current I. All right, what's the equivalent? Well, it's this R and C in parallel. So it's R Thevenin multiplied by 1 over j omega c over R Thevenin plus 1 over j omega c. Multiply numerator and denominator by j omega c. We just get R Thevenin, j omega c R Thevenin, and plus 1. The magnitude of this is just the resistance at angle 0. Then we take the imaginary part, square it, take the real part, square it, and then take the square root. And then the angle is the arctangent of the imaginary term divided by the real term. So it's the arctangent of omega c times R Thevenin. Multiply this by I sub A at angle 0. So then I've got my current times my impedance. And I'm just going to clean this up a little bit. So I've got the magnitude of I sub A and R Thevenin together. The two angles of 0 and 0 add to 0. Our denominator magnitude. And then the negative of the denominator angle would be the overall angle. That would be a minus the arctangent of omega c times R Thevenin. Then in step 3, then we're going to put the cosine of omega t between the magnitude and the angle. So it's right over here. In our formula above, we used that tau is equal to R Thevenin times C, or that R Thevenin is tau divided by C. So I have I sub A, and R Thevenin then would be tau divided by the capacitance C. And then we have here omega squared, and then we've got R Thevenin times C, which is tau squared. And then we've got the term right here, which is C times R Thevenin, which is also equal to tau. And this is the same formula we had up on top. Now it's interesting to note that it took 4 pages to derive that complete response. And we just had here in just really a half a page the forced or steady state response. And as you can see, we can save ourselves a lot of time by using the phasor approach if all we're interested in is the steady state value. And this is supplemental problem 8.9.